Greetings to all and welcome to this lecture. We are in module 7, lecture number 1. Here we will discuss the second part of strong inversion analysis, which we started in previous lecture. In this lecture, we will cover the body reference simplified model and the source reference simplified model, and we will see how we can derive the drain current equation considering body reference and source reference, which means in one you are considering the substrate or body as a reference terminal, and in one you are considering the source as a reference terminal in your 4 terminal MOS, which is source, drain, body and gate. These are the learning outcomes of this lecture, which helps you to understand what is the difference between body reference and source reference model, why body reference and source reference models are separately needs to be discussed, how we can approach the simple form of drain current equation which can be used in our simple hand calculations. So let's start this lecture with a quick recap which we started in our previous lecture considering the strong inversion operation. We said that our MOSFET is in strong inversion if its heavily inverted end of the channel is in strong inversion. So if my source is heavily inverted and VDB is increased, so if VDB is increased to over VSB, then the inversion charge near the drain end is less, and hence you have a tapered channel like this, correct? In both ends we do have charges, and then we can say the operation of MOSFET is strong inversion. We started our analysis considering that the value of VDB is not so high that it crosses the pinch off, and hence we derive the equation for IDSN. Here N stands for non-saturation. We said that in this region of operation the drift current dominates, and we calculated this complete equation as W by L into mu into COX dash into VGB minus V flat band voltage minus phi naught into VDB minus VSB minus half of VDB square minus VSB square minus 2 by 3 gamma VDB plus phi naught to the power 3 by 2 minus VSB plus phi naught to the power 3 by 2. This equation is applicable here. Then we said what will happen if VDB is increased beyond a value of VQ, meaning at this value my surface potential is approximated getting to pinned, because VDB is increases and hence the surface potential psi SL shows this trend. So this is the value of VW and this is the value VQ. So at the pinch off region we define this pinch off region as the slope of the current DIDSN divided by dVdB is equals to 0, which was nothing but V pinch off is equals to minus gamma by 2 plus square root of gamma square by 4 plus VGB minus V flat band voltage whole square minus phi naught. Now we have done this analysis in previous lecture considering that we do have a pinch off voltage which decides that whether my current is IDSN or I dash DS, where I dash DS is the saturation part of the current. Let us simplify the analysis or the model further by considering body reference and source reference conditions. So what is body reference? You remember we said that in our previous equation there is square root term VDB square minus VSB square is coming, square term is coming, and also VDB to the power 3 by 2 or 1 by 2 will also come. In previous analysis we said that the term of 1 by 2 and 3 by 2 is coming because of bulk charge, which was given by minus gamma Cox dash square root of psi s. So to avoid this complication, we said that we'll go for linearization. Linearization around a point which we termed as expansion point. So if we will plot minus qb dash by Cox, then this point is psi s 0, this point is psi s l, and we will linearize around a point psi s e. We already mentioned here also, it is important to note that psi s a is neither the potential at source nor the potential at drain and nor the potential in the channel. It is just an expansion point. Around this expansion point, we expanded our relation qb dash by Cox dash as gamma times square root of psi s e plus gamma by 2 times of square root of psi s e into psi s minus psi s e using Taylor expansion. Now, for a body reference model, we said that psi s e is nothing but psi s 0 plus psi s l divided by 2. This is what we derived for a body reference model, and this factor is also defined as alpha, which is alpha is equals to 1 plus gamma divided by 2 times of psi s m. Here m stands for mean or average, which was taken for body reference. By following these analysis, we also derived the current equation in strong inversion, which was drift dominant equation, which is nothing but IDS1 is equals to W divided by L mu into Cox dash into VGB minus V flat band voltage minus psi s e minus gamma root psi s e into psi s l minus psi s 0. Considering the strong inversion, you can put all this model, all these values here, where psi s e is nothing but what? Psi s 0 plus psi s l. Psi s e is psi s m when we talk about body reference. Here psi s l is nothing but phi naught plus VDB, and psi s 0 is nothing but phi naught plus VSB, which we have already discussed in previous lectures. Correct? Keep these values in this equation, you will get this equation. IDSN, which is N stands for non-saturation. We are considering only the drift current is dominating, and hence we are ignoring the diffusion part. So instead of writing IDS1, we are just considering IDS, and N stands for non-saturation region. W by L mu into Cox dash, VGB minus V flat band voltage minus psi s e. So what is psi s e here? It is psi s 0 plus psi s l divided by 2, which is nothing but phi naught plus VSB plus phi naught plus VDB divided by 2, and hence 2 phi in the numerator with 2 gets cancelled from the denominator, you will get minus phi naught, and the another term will VSB plus VDB divided by 2 minus of this. So you can see this is a very simpler equation of drain current, and there is another term coming up which is VDB minus VSB, because at the outside psi s l minus psi s 0 is given. So though it is simpler, but having some drawbacks. What are the drawbacks? If you see closely, we cannot say this equation in terms of symmetricity of the device, because here there is VSB and VDB are coming in the square root, and that too in terms of mean. So you can not extensively decide that which terminal is source, which terminal is drain. That is the first drawback of this equation or this model. That is what we need to take care of, in which region of operation which model is best suited. However, always some models or every model does have some good insights. What is a good insight here in this model of body reference? Though I cannot define the symmetry of the device, but I can easily define the other property of the drain current and the terminal voltages. Let us consider that VDB and VSB are increases in opposite direction or changes in such a way that the mean is not getting disturbed, and hence the value which is written in this parenthesis is almost constant, because we are assuming this is not changing, this is not changing, this is constant, this is constant. So this parenthesis value is only dependent on VGB. So let me define this as some function k which is a function of VGB, and there is another term which is VDB minus VSB. So I can simply write that current IDSN is directly proportional to the difference between VDB minus VSB. This is nothing but an Ohm's law, meaning the current which is flowing between drain and source defined by the difference between drain to body voltage and source to body voltage is linearly rising when VDB is greater than VSB, but not so high value. So you are in non-saturation. So this defines that my MOSFET acts as a resistor. Here K times VGB is nothing but 1 over R, right? And hence I can simply define my MOSFET acts as resistor. The good part is the resistivity of this resistor is controlled by the applied gate voltage, and hence this is a very important property of MOSFET in the linear region. So when you plot the current equation with respect to VDB, we found that the current is linearly rising in the initial part of VDB. So that linear graph shows that my MOSFET acts as a resistor. Now you cannot define this property by using this equation which is having symmetricity, because you can show that yes, which is my source and which is my drain terminal, and you can interchange. However, you cannot define the property of this resistance or the resistivity by using this square law or power of 3 by 2, correct? Now let's see what will happen when we go for a source reference model. We have also defined that this linearization of bulk charge can be done based on some expansion point. One expansion point what we have already mentioned as psi SE is equals to psi SM, which is nothing but average of these surface potentials. Another surface potential point, another point of expansion considered as psi S0. You remember we plotted 3 lines which we called it as A, B and C. Corresponding to the source reference model, we said that alpha is defined as alpha 1, which is nothing but 1 plus gamma divided by 2 times of root psi S naught. Correspondingly, we derived the equation for the drain current in strong inversion, which is drift dominant, and hence IDS1 can be given by W divided by L mu into C aux dash VGB minus V flat band voltage minus psi S0 minus gamma root psi S0 into psi SL minus psi S0 minus alpha by 2 psi SL minus psi S0 whole square, where alpha is given by this quantity. Here psi S0 is the surface potential near the source end, and this is used as an expansion point. If we put psi S0 now in terms of terminal voltage, psi S0 can be simply replaced by psi 0 or phi 0 plus VSB. You can rewrite this equation here. If you closely see this term VSB plus phi naught plus gamma times of root phi naught plus VSB plus V flat band voltage is nothing but VMB or VTB, the threshold voltage with respect to body, the body as a reference. However, in previous lecture we have discussed that if I want to represent this in terms of source, I need to rewrite as VTB minus VSB, and this threshold voltage is with respect to source. Here the reference is source, not the body, and hence this equation can be represented as Vt, and VGB minus VSB is can be written as VGS. So this equation can be written as VGS minus VTB or VT with VSB, correct. So in general, we need not to show again and again that with respect to what we are actually calculating. If it is VGS, it is understood that VT is calculated with respect to source. Now this term VDB minus VSB is again what? VDS. We have already discussed VDS is nothing but what? VDB minus VSB. You are just changing the reference point. Earlier the reference point was body, now the reference point was source. Similarly, this is what? VDS. So a simple closed form equation is coming into picture, which shows that my IDSN is equals to W divided by L mu into COX dash into VGS minus VT wholes into VDS minus alpha by 2 VDS square. If you see closely, this is simple equation which we use in our hand calculation, but you see what is the story behind the depth of this derivation. We have to have a lot of approximations like body reference, source reference, and then we are actually coming with this closed form equation which we are using in general for hand calculation for MOSFET analysis. This equation is valid for non-saturation region where VDS is greater than VGS but with some small value. What is that value? We define in terms of VDB that VDB is greater than VSB but VDB is less than pinch off voltage. Let's move further and ask a question that can we not derive this equation by simple calculation instead of going again for the surface potential charge equations as well. So yes, we know the equation IDS is equals to what? W divided by L mu into COX dash or mu into integration minus of QI dash into dVCB. I can use the same equation and calculate the current where QI dash now here is linearized QI dash you need to take care of. QI dash is nothing but minus of COX dash into VGB minus V flat band voltage minus psi S minus QB dash by COX dash, where QB dash is minus QB dash. So QB dash is nothing but minus of COX dash into gamma into root psi S, but now you have linearized this. So you need to replace as minus COX dash into gamma root psi S E plus gamma divided by 2 times of root psi S E into psi S minus psi S E. As we are talking about source reference model, this psi S E is nothing but what? Psi S 0. So you can replace as QB dash is equals to minus of COX dash gamma times this will become psi S 0, and if you want to represent in terms of terminal voltage, it is nothing but phi naught plus VSB plus gamma divided by 2 times of root of phi naught plus VSB. Now psi S, if you want to represent the surface potential in general x, right, it means along the x if you want to represent this, then you can rewrite as phi naught plus VCB as a function of x minus this psi SE is phi naught plus VSB. Again this term can be replaced as alpha minus 1, where alpha was given as 1 plus gamma divided by 2 times of root psi SE. If you keep psi SE as psi S0, then this become alpha 1. We have already discussed this fact. So out of this you will get this equation in terms of VCB, which is a function of x. You keep this value here and put that equation in this equation, ultimately you will ended up with the same solution. So we need not to go again for a modeling of surface potential. We can directly calculate the current of drain to source by using this equation, where these quantities we have already defined in previous slide, that Vt is nothing but V flat band voltage plus phi naught plus gamma times of square root of phi naught plus VSB, where you are calculating the threshold voltage with respect to source as a reference. Whereas if you need to calculate in terms of body as a reference, you need to add VSB, right? Now let's see again that equation what we just derived as IDSN is equals to mu into COX dash into W divided by L VGS minus VT into VDS minus alpha VDS square by 2. How can I calculate the peak value or the saturation value? We have already discussed that we can calculate the saturation value by considering the slope of this curve is what? 0. So I can simply do that IDSN. Now as we are representing in terms of VDS, considering source as a reference, VDS is equals to 0. If you differentiate it, you will get VGS minus VT minus 2 times of VDS divided by 2 into alpha is equals to 0. So VDS is equals to VGS minus VT divided by alpha. So this is this value, we called it as VDS dash. VDS dash is the value of VDS at which the pinch off occur, beyond which my current is getting saturated. Now can I calculate the IDS dash by using here? So yes, at this value of drain voltage VDS dash, my current is getting saturated. So ultimately you can put back this equation in the current and you can calculate this, right? So IDS dash is equals to W divided by L mu into COX dash VGS minus VT. Now you are actually calculating the current exactly at this point, which is constant after this point, right? So you can keep this VDS value as VGS minus VT divided by alpha minus alpha into VGS minus VT by alpha whole square divided by 2, correct? So if you solve these equations, this is alpha square, so in the denominator you will get alpha, and then if you take it out you will ultimately ended up W by L mu into COX dash divided by 2 alpha VGS minus VT whole square. I think now you can relate this a simple formula which we use for our hand calculation, which says that in linear region or in non-saturation region the current formula was given by this, however in saturation the current was given by this. Okay, let's plot this graph for different reasons of operation. So we said that if VDS is as a reference value, this will start from 0, and this shows that the model which we derived is applicable for a smaller value of minus VDS also, right? So if you reduce the VDS value for a smaller value till VSB, then this model holds good. This is a linear region of operation which can be given by this equation when VDS dash point is less than or equal to VDS, okay, and when VDS is greater then you are in saturation. So we can simply define if VDS is greater than equal to VGS minus VT by alpha, then you are in saturation. If VDS is less than equal to VGS minus VT by alpha, then you are in linear. Let's plot this equation again. So as it is plotted here, I am just plotting from the scratch, considering this axis is VDS and this axis is IDS for various values of VGS. Let us consider a first value of VGS as VGS1. So what is this point? It is VGS1 minus VT by alpha. Now this current is again what? Quadratically dependent. So let's say this point is VGS1 minus VT whole square. So we are just plotting an approximate value. So this point is like this, and till this point my slope lies linearly, and after that it gets saturated, correct? Let me change the color of pen to include another value of VGS2 which is greater than VGS1. Obviously both point will shift. First, if VGS2 is greater than VGS1, this new point will be what? VGS2 minus VT divided by alpha, and this point will be quadratically shift. It means if it is 2, that will be 4, if it will be 4, that will be 16. So this point will be quadratically shift as VGS2 minus VT to the power of 2, and so this is the new point and this is the graph. That is what we are getting here. So for various values of VGS, the difference between this is quadratic. Correct? And similarly these points will shift it to the right. This is a boundary which defines that whether you are in saturation or non-saturation, which was defined by VGS minus VT by alpha. Very strictly speaking, this is not a stringent boundary because you can simply see it depends on alpha. In simple hand calculation, we generally consider VGS minus VT into VDS minus VDS square divided by 2 into mu into COX into W divided by L is equals to ID. But this is not the correct equation because we have seen that what is the role of alpha. That is what we will discuss in our next lecture also. What is the major role of alpha in optimizing or deriving the closed form equation of current. Now here another factor I need to mention, that it depends on VT, the threshold voltage, which is nothing but what? V flat band voltage plus phi naught plus gamma times of VSB plus phi naught, meaning this value of threshold voltage is dependent on VSB. So how can we incorporate or how can we justify this VSB value? Let us consider the plot of 2ID VD curve for different value of VSB. If VSB is 0, the plot will be similar as what we have discussed earlier. But now what will happen if you increase the value of VSB? First of all, if you increase the value of VSB, right, the threshold voltage value will be shifted up, and hence this point, what we said is a saturation point, VGS minus VT divided by alpha will shift. The second thing is the value what we derived in the y axis is what? Approximately VGS minus VT whole square. This is approximate value of current, and hence if threshold voltage is increases by increasing VSB, then this factor will decrease and hence the current gets decreased. That is what you can see. If VSB is higher, right, source to body voltage is higher, it is actually affecting the current. So you can see the graph is get shrinked for this reason what we have discussed so far. Here I need to mention that this solid line is the model what we derived so far considering several approximation, and the dotted line shows that the complete region model what we derived in previous lecture, complete all region model, right. You can see that the accuracy of the simple model is very much good when we compare with the all region model, and hence that is what the reason to capture the modeling in different region of operation separately, like I mentioned strong inversion, weak inversion and moderate inversion. So let me summarize here. In this lecture we have seen that in strong inversion we can define the current by considering source reference or body reference model, where only we have considered the drift component. We have also said that different model give different intuitions, like with the body reference model we said that it shows that my current is linearly rises with drain to source voltage, and hence it shows that MOSFET acts as a resistor. However, when we shows with respect to source as a reference, then we derived an equation which was nothing but IDS is equals to W divided by L mu into COX dash into VGS minus VT VDS minus VDS square alpha by 2. It is very important to note that this equation is governed by alpha. What value of alpha you are taking, it decides the accuracy of this model. That's what we are going to discuss in next lecture. So we'll stop here for today. Until then, take care.